Welcome everyone. In this video, I will be covering 15.6 triple integrals. Before we introduce triple integrals, let's review double integrals that we covered in the previous sections. If f of xy is more than or equal to 0, and if the limit exists, then Riemann double sum, sigma I varying from 1 to m, sigma j varying from 1 to n, limit is m and n approaching infinity, f of xi yj dA, which is written as double integral over r, f of xy dA, which represents a volume under the surface f of xy over the region R. So this can also be written as f of xy dA. We normally write this as dA is either dy dx or dx dy. We all know that. This is what we had been doing in the previous sections. Here, dA denotes a small change in area. dx and dy represent small change in x and y. How do we extend this idea of this double integral to triple integrals? If f of xyz is continuous over a bounded solid region E, then the triple integral of f over E is defined as limit L, M, and N approaching infinity, triple sigma I varying from 1 to L, sigma j varying from 1 to M, sigma k varying from 1 to N, f of xi yj zk delta v, which is written as triple integral over the solid region E, f of xyz dv, which in turn can be written as triple integral over E over the solid region f of xyz dx dy dz in any order as long as you have the limits corresponding to the variable appropriately. For triple integrals, E is a 3D region. So it's a solid. For double integrals, R is a two-dimensional region. So we have seen double integral over a rectangle. We have also seen double integral over a general region. So R doesn't mean rectangle here. It could be any two-dimensional region. For triple integrals, there are 6 possible orders of integration. They can be dz dy dx, or dz dx dy, or dy dx dz dy dz dx, or dx dy dz dx dz dy. So we have 6 possibilities, or 3 factorial possibilities. Evaluating triple integrals over a rectangular box. Just as we defined double integral over a rectangle, where we found those problems were simple because of the definite limits for the integrals. A Fubini's theorem for triple integrals. If f is continuous on a rectangular box B, which have dimensions x variation from A to B, y variation from C to D, z variation from R to S, then triple integral over the ball B, f of xyz dv can be written as triple integral of f of x, y, z dx, dy, dz. So dz is the outermost And that corresponds to these limits. So it is R to S to Z. Then we have to write down the limits for Y, which is the second one. So the middle integral, that is from C to D, C to D. Then the innermost is with respect to X. Innermost is with respect to X. And X variation is from A to B. So giving the limits appropriately in triple integral is very important. Evaluating triple integrals over a general bounded region E. Exactly similar to how we defined double integrals over general region. If f is a continuous function, f is continuous on a solid region E defined by a less than or equal to x less than or equal to b, y lying between h1x and h2x, two continuous functions, and z lying between g1 of xy and g2 of xy, where h1, h2, g1, g2 are all continuous, then triple integral over E f of xyz dv is defined as the outermost should have definite limits, which is a to b. So it is actually f of x, y, z. Then you are going to integrate with respect to z, which is the innermost. Then the second one is with respect to y. The last one is with respect to x. So this x here, dx, corresponds to the x limits, which are a to b, the outermost. Then dy, the inner one, y runs from h1 of x to h2 of x between two functions. Then we have z, which is the innermost. Z variation is from g1 to g2, g1 of xy to g2 of x comma y. Note, innermost integral is integrated with respect to z, what we mentioned there, and the limits for z are functions of x and y. Then it is integrated with respect to y, and the limits of y are functions of x. And lastly, the outer is integrated with respect to x, and the limits are constants. As there are 6 possible ways for the order of integration, the limits to the variables must be adjusted carefully. We'll try this example 1. Evaluate the triple integral over the ball B, x, y, z square dv, where B is a rectangular box given by B equal to set of all x, y, z, where x lies between 0 and 1, y lies between -1 and 2, and z lies between 0 and 3. So it is a triple integral over a ball. So we have all the limits of xy. XYZ limits are all definite limits. So the problem is going to be much simpler than problems that involve variables in which are functions of another variable or variables. So let's try this one. Step 1. Write down the triple integral over the ball x, y, z square dv, which can be written as triple integral. Here, the order in which you write dx, dy, dz does not matter because all are going to be definite limits. So x runs from 0 through 1, y runs from -1 to 2, z runs from 0 to 3 as given in the problem. And here it's x, y, z square. In this particular problem, we notice that the you have product of functions, a product of variables x, y, and z square. And each one of them vary over definite limits. Product. So if it was sum, you could not have separated them. So you can separate the variables in this case. So I'm going to call the given integral as I, just for convenience. So I is integral 0 to 1 x dx, then integral -1 to 2, that is integral for y, then you have y dy, then integral over z, z varying from 0 to 3, z square dz. So we did this by separating the variables. Note, we were able to do because the limits are definite limits, or constant limits, constant lower bound, constant upper bound. The limits are definite, therefore we are able to separate them. Also the function and the integrand is a product and separable. That's why we were able to separate these integrals like this. The first integral of x, which is x square over 2 between 0 and 1. Second one is y square over 2 between -1 and 2. Third one is z cube over 3 between 0 and 3. So the first one is 1/2. Second one is 4 over 2, that will be a 2. Then you'll have -1 square. So minus of -1 square, it's 1 over 2. Then you have a 27 over 3, that will be a 9. Thus we have 1/2. This will be 3 over 2 times 9. So it is 27 over 4. We will continue with this material in the part B of concept video for section 15.6 triple integral. Make sure to watch part B.